Okay, in this module, we're going to go ahead and focus on balancing chemical equations. So we should be able to write a balanced equation given formulas or names. If we're given the names of chemicals, we should be able to give it to the formula and balance it as well. We should be able to include phase notation, which means telling me is something in the solid phase, liquid phase, gas phase, or aqueous phase. Aqueous means dissolved in water. We should be able to, balance any combustion reaction as well. And we definitely need to keep track of law of conservation of mass. This is probably one of the most things that are missed by students. Balancing equations is what does keep track of law of conservation of mass for us. We cannot create things nor destroy things. We can only convert things from one thing to another. But the starting and ending has to be the same. We had something in, we have something out. So chemical reactions or chemical equations. A chemical equation is a symbolic representation of a chemical reaction. And yes, this is written just on this page as well here. But I think it's important for students to understand that. What is a chemical equation? Because we will often say equation and reaction interchangeably when we're talking or when we're teaching in class. And so I need you to realize that we're using those terms interchangeably, even though an equation, we use these because of mathematically, but they are representing that reaction that's happening. So, writing and balancing chemical equations. We have to do this to be able to correctly calculate the quantities in chemical reaction. After this, just a little bit further into this chapter, we're going to start getting into stoichiometry. Which I call stoic, to abbreviate. And stoichiometry is how I can determine how much of one substance is produced or consumed based on other key pieces of information from the reaction. So if I say I'm going to react 5 grams of oxygen and I want to know how much iron oxide I can produce from that, that is stoichiometry. In order to do that, I have to have a balanced chemical equation. The equation itself, again, symbolic representation of a chemical reaction. So we will often use reaction equation interchangeably in terms. The reaction is technically what's actually happening, what the molecules, the ions, and the particles themselves are doing. The equation is how we are representing it on paper. It's in the form of symbols and formulas, reactants provided on the left, products on the right, and arrow in the middle. And that isn't always things. We see here our reactant side, our product side, and an arrow in the middle. You will see a little bit in Chem 1, definitely in Chem 2 we studied a lot, reactions that we consider to be reversible. We call them either reversible or equilibrium reactions. We're going to see both, okay? It's still the same setup. Symbolically, we still always consider it to be a reactant on the left-hand side and a product on the right-hand side, no matter what, even if the reaction goes the other direction. Then I would write the reaction the other direction, and it's still always reactant on the left, product on the right. Reactants are the species that are always left of the arrow. They are initially present in a chemical reaction, but they're consumed or reacted during the reaction to make or produce those products. The products are the substances that are formed or produced in a chemical reaction, and we will always find those on the right side of the arrow. How much product I can make is limited by how much reactant I have. So the amount of reactant I have controls how much product I can actually produce. Okay, so your book has a set of rules that we can follow for balancing equations. And I recommend going through this and following it until you start to get your pattern down yourself. Eventually becomes second nature. Most students do pretty good with balancing equations. They don't really struggle with it too long, but these are the rules you need to follow until you get that pattern down. Identify your most complex substance. Beginning with that substance, choose an element that appears in only one reactant and one product if possible. Adjust the coefficients to obtain the same number of atoms of this element on both sides. Balance your polyatomics, if present, as a unit when possible. If the polyatomic stays together, keep it together. If it splits apart, then we look at the individual atoms. Balance the remaining atoms, use fractions if necessary, and you'll often see this happen with diatomics. Not always, but often. But again, if a fractional coefficient has been used, multiply both sides of the equation by the denominator to obtain whole numbers for all coefficients. You are not allowed to leave fractions in your balanced equation. There's one very specific case of an equation where fractions are actually required, but that is for a formation reaction, and we don't even learn those until the thermochemical chapter, or thermochemistry chapter. So no fractions in your balanced equation. You will have to multiply through by a factor to get rid of your fractions. Check your work. Make sure that by counting the number of atoms of each kind of both sides of the equation, that your equation is in fact balanced. By counting, I mean like if I look at this reaction up here, I would have 1 carbon, 4 hydrogen, and 2 oxygen on my reactant side. Again, this 4 only goes to the hydrogen, this 2 only goes to the oxygen. The other side, I have 1 carbon, 2 oxygen, 2 hydrogen, and 1 more oxygen. So this reaction is not in fact balanced, and I would actually have to balance the reaction. So let's go ahead and practice that on the next slide where we have a little bit more, or well, one more slide after this where we have a little more room. We do need to practice counting the atoms. So remember, a coefficient, the number out in front, is applied to all elements in the formula. Here's my coefficient. If I wrote it like this, this means I have 2 times Al2, 2 times S3s, 2 times this. Now I'll talk about the aluminum in just a sec. But the coefficient out front, again, that's what it's called when it's out front like that. It's called a coefficient. This is called your coefficient. So if I have, say, 3 KMnO4, that means 3 times my potassium, 3 times my manganese, 3 times my oxygen, but I have a 4 down there, which means 3 times 4 is 12 oxygen. A subscript, your subscript is what's listed below the elements here. The subscript applies to the element it follows, not the whole molecule. So here, I don't have any subscript after the potassium, I have 1 potassium. I don't have any subscript after the manganese, I have 1 manganese. I do have a 4 after my oxygen. That means I have 4 oxygens. Now if a subscript follows a parentheses, it counts for the entire polyatomic. And that's what I see here on the aluminum sulfate. This applies to this entire polyatomic, which means I've got the 2 in front of the aluminum, 2 aluminum, but the 3 in front of the polyatomic. So I've got 3 sulfur, but 3 times 4 for the oxygen. So that goes to that, this goes to the entire thing, but I did tend to that 4. Now, looking back at this aluminum sulfate up here, I've got this 2 in front. If I had this written down, this would be 2 times 2 for aluminum, overall 4. It would be 2 times 3 for sulfur, overall 6, because the 2 is distributed through, but this 3 is also distributed through. And this would be 2 times 4 times 3 for oxygen, overall 24, because I've got the 3 times the 4, which is 12, times the 2, giving me 24. Okay, so let's look at some symbols, because we do have to be able to write the phase notation as well, and so you should be able to write these in your reactions. Some of these you're going to get just from the context of the question itself, some of these you're going to get as you learn more chemistry, but you should be able to write the phase notation for the species you have as well, and that is important for the overall reactions. Notice these are all lowercase, so you should have lowercase letters written. If you have a G, it stands for gas, L stands for liquid, S stands for solid, and AQ, that is a Q, is aqueous. This means it has been dissolved in water. We do a lot of aqueous in Gen Chem. You may also see things written above your arrows. So you may see an arrow with a little triangle above, or a little arrow with an HV. Looks like a V, it's H nu is the actual symbol, it's a Greek letter above. If you see the little triangle, it's representing heat. It means that heat was applied to the system. If you see the little HV, it just means light. So like UV light was applied to the system. Don't worry too much about it. It's required for the chemistry of the reaction, but it doesn't affect the balancing. We can spend a lot more time talking about catalysts in Chem 2, but catalysts are something that will speed up the reaction for us and find a quicker pathway to make it happen. And so oftentimes catalysts will be written above the reaction like this. Catalysts are not considered reactants or products. So they are something separate from the reactant or product of the actual reaction. They're not required for the reaction to occur per se. They find a quicker way for it to happen, so reactions may not happen without it, but they're not actually consumed in the reaction. They're there at the beginning and the end. So they will be written above the arrow like this. So here, like where I've got MnO2, it's written above the arrow. It's not in the balanced equation because it is a catalyst. It is not a reactant or product. So let's look at some balancing. So remember that we need equal number of elements on each side of the equation. This reaction, this first one we're going to look at is here, and this one, it appears like it's balanced. Let's just go ahead and make sure. Well, I've got iron, I've got carbon, and I've got oxygen. I've got a 4 in front, which means I have 4 iron, 4 in front, 4 carbon. I've got 3 oxygen here, but a 4 in front, so I've got 12 oxygen here. I have another 2 oxygen here. Overall, I have 14 oxygen on my reactant side. On the other side, I'm going to write the elements in the same order. So I'm going to write iron, carbon, oxygen, iron, carbon, oxygen. And I'm going to compare them. I've got Fe2O3. So practice thinking about what these things are called. Fe2O3, iron 3 oxide. But I've got a 2 in front. So that means I have 4 irons. I've got 3 oxygen here with a 2 in front. That means I have 6 oxygens. 4 in front here, 1 carbon. That's 4 carbons overall. And I've got 2 more oxygens in my CO2. Remember, CO2 is carbon dioxide, but times that 4 gives me 14. And I check, and 4 iron, 4 iron, 4 copper, 4 copper, 14 oxygen, 14 oxygen. My reaction is indeed balanced. Let's look at this next one. Fe3O4 plus H2 giving me Fe plus H2O. So I've got iron, oxygen, and hydrogen. Iron, oxygen, and hydrogen. Careful, because here if I wrote iron, hydrogen, oxygen, they're not going to be the same down here, and then I'm likely to mix them up when I'm balancing the reaction. So I always write the elements in the same exact order. Here I've got 3 iron, 4 oxygen, 2 hydrogen. Here I have 1 iron, 1 oxygen, and 2 hydrogen. I have to balance them out. I can start with the iron or the oxygen first. The hydrogen appears to be balanced. I'm going to mess that up in just a sec by balancing everything else. But let's go ahead and give this... let's start with the iron. 3 iron, 3 iron. The reason I'm starting with iron is because when I balance out my irons, it may affect my oxygen. And plus it's listed first. I'm just going to start with what's listed first. I'm going to say times 3. Okay? If I give a 3 in front of this iron here, that would give me 3 irons on each side. And I will rewrite the balanced equation at the bottom in a minute. Okay, cool. That balanced my irons. Didn't affect anything else. That's good. Let's balance my oxygens. If I put a 4 in front of this water, that's going to give me 4 oxygens on each side. Perfect. That did, however, mess with my hydrogens. Now I have 8 hydrogens over here. I need 8 hydrogens over here as well. So in the total of the balanced equations here, I will have Fe3O4 solid, 4H2 gas, giving me 3 moles of Fe solid. Now we're out of room. I apologize, I hate splitting things through the boxes, but I'm going to run out of room otherwise. Plus 4 H2O liquid. And when I look at my overall equation here, I've got 3 iron, check. I've got 4 oxygen, check. And I've got 8 hydrogen, check. The reaction has been balanced, and so I know that 1 mole of Fe3O4 reacts with 4 moles of H2 to produce 3 moles of Fe solid and 4 moles of H2O liquid. Let's work 2 more examples. When butanol, C4H9OH, is burned in oxygen, CO2 and water are the products. What is the coefficient in front of the O2 in the balanced equation using only whole numbers and the lowest whole number ratio? I'm going to make this bigger so we can focus on this one. Okay, so it tells me I have butanol. So I've got C4H9OH. Burned in oxygen. That means O2. Remember, oxygen is one of your diatomics. Gives me CO2 and water. It's not giving me an idea yet what my phases are. And we'll deal with that when we do the next module, when we actually work some stuff in class, focusing more on that. But so if you know what they are, great. If you don't, okay. We know oxygen is gas. We know CO2 is gas. Water could be gas or liquid. When you burn it, it's probably going to form a liquid, condenses back down to a liquid, and butanol is actually a liquid. But again, without context in the question, you may not know that one, and that's okay. Let's focus on balancing. I've got carbons, hydrogens, and oxygens. Carbons, hydrogens, and oxygens. I'm going to go ahead and move this out a little bit for some space on the coefficients. Here, I've got 4 carbons. I've got 9 plus 1, 10 hydrogens. Careful not to miss that hydrogen. A lot of students will. They won't add them together. The other thing students are going to miss is this oxygen right here. They're going to not see it in the middle. So don't miss that oxygen in the middle. 1 plus 2. I've got 3 oxygens. Other side, I've got 1 carbon. 1, 2, 3. Oops. 2 plus 1 is 3. Oxygens and 2 hydrogens. Let's go ahead and balance our carbons first. I'm going to say times 4 here. Gives me 4. Put a 4 in front of there. Now that does mess with my oxygens though. I now have 4 carbons, but I now have 8 plus 1, 9 oxygen. I have 10 hydrogen on one side, so I need 10 on the other, so I'm going to say times 5 here. But that also messes with my oxygen. 8 plus 5 is 13. I have 3 on one side, I have 13 on the other. Now, how am I going to balance this out? Well, this is where students are going to get messed up. I need you to think about that there's a 1 here, okay? The 1 versus the 2. Students, again, are going to forget the 1 right here, and they're going to mess with this for a long time. I need you to recognize that there's a 1 on that side, and C4H9OH is happy. The carbons are happy. The carbons are balanced. The hydrogens are balanced. That means that I still, if I count that out, I need 13 oxygens total, right? 13 minus 1, I need 12 oxygens somewhere else on this side. I have an O2 here. If I put a 6 in front of that O2, that gives me 1 plus 6, or sorry, 1 plus 12. I can do math. 6 times 2 is 12. I apologize. 1 plus 12 giving me overall 13. I will do other examples in class where we have to use fractions, but this is not one of the cases we're going to need a fraction, okay? Make sure that you're paying attention and not forgetting when you have something like the oxygen right here. No color I use is going to work out well on gray. But the oxygen right here, don't forget that oxygen. I did not have to use fractions because I had the oxygen right here. Now, if you're ever unsure, go ahead and just erase everything and rebalance it quick. Just make sure you're correct. Just check yourself, because if this is not correct, then none of your stoichiometry is going to be correct, and you're going to get the entire question wrong, and that's just going to be sad. So, 4 carbon, 9 plus 1, 10 hydrogen, 1 plus 12, 13 oxygen. 4 carbon. 4 times 2, oxygen. 5 times 2, or 10 hydrogen. Plus 5, 13 oxygen. Now here's the biggest trick of all. The question specifically asks me, what is the coefficient in front of the O2 in the balanced equation? So some students will just give me the balanced equation, and that's great, except that's not what it's asking me for. The question itself is saying, what is the coefficient? The coefficient in front of the O2 in the balanced equation is 6. That's what it's specifically asking. Okay, let's do this last problem. What numbers belong in the blank spaces to fully balance the following reaction? We've got Fe solid reacting with Cl2 gas to produce FeCl3 solid. So iron solid, chlorine gas, remember chlorine is one of your diatomics, forming iron 3 chloride. Again, diatomics, and I know I mentioned that before because of oxygen, but remember your diatomics. You've got H2, then N2, O2, F2, Cl2, Br2, and I2. I intentionally wrote it this way because when you look at the table, you've got hydrogen off by itself, and then you've got these 6 that form a number 7 on the table, and there are 7 total diatomics. So in this question, I don't have to give you the formula. I could say solid iron reacts with chlorine gas to form iron 3 chloride, and tell you that the iron 3 chloride is a solid, or somehow make it known in the question it's a solid, and you should be able to give me the phase notations as well. But back to it. Let's balance it. I've got 1 iron, 2 chlorine, 1 iron, 3 chlorine. You've got that 2 to 3 ratio going. Make it a multiplet. I'm going to put a 3 here, giving me overall 6 chlorine. I'm going to have to put a 2 here, give me overall 6 chlorine. Give me a 2 here for iron, put a 2 here, and my equation is now balanced. So this is, again, just an introduction to balancing. We will do some more balancing in the next video, which is also going to be done in class. It'll be more practice, looking at some more examples, etc. But to get you down, get you comfortable starting to balance things, these are the easier examples to do and things to watch out for.